arrows are a little bit misleading. There's nothing moving. These are not flow lines. These are simply lines that show you the vector direction of the point in the field at that point. So there's nothing moving around those lines. Also, you may think, well, look, there's open field lines at the top and open field lines at the bottom. Yeah, sure, because we don't have a big enough piece of paper. You can draw open contour lines on a map of a mountain, and if your map isn't big enough, you will see 1,000 feet goes off here, and it's off, and then 1,000 feet comes back here on the bottom. That's exactly the same as we're seeing here. Actually, this is, if I can get it to show. Yeah, this is more like what a magnetic field might look like. Even that's not right, because there's no discrete quantized steps. It's a smooth continuum. But wouldn't you rather draw the one on the left? It's a hell of a lot easier than drawing the one on the right. But don't let that artifice make you, there's a word that I love. It's called reify. Don't let a concept become a real three-dimensional object. Pinocchio is a wooden puppet. He's not a boy who can do things. So is a magnetic field line, just an abstract concept. This is a model for the double radio source galaxy that Alfvén came up with. It's, I don't know if you can see it, it's supposed to be Cygnus A. The blobs on the left are what we sort of see about Cygnus A. The galaxy itself is this little thing in the middle. And these are the radio emission patterns seen by the Very Large Array in Socorro, New Mexico. Alfvén said that, by the way, I should have said this when we were talking about double layers. If you think about that big drop in voltage and the current that's going through there, the product of volts times amps is watts. So a double layer is where most power is released. And it's released in a plasma as radio noise. So a double layer is almost always noisy. You can hear it by its radio transmissions. And you can see that if indeed this model is correct, it shows current paths, which are sort of like two cups. It's kind of like an hourglass kind of thing. There's what the picture really looks like. And of course, there's also that jet, that highly collimated jet that goes out from the central galaxy in both directions, stronger to the right in this picture. And so the astronomers go through all sorts of tortuous logic, Schwarzschild event horizons, and various types of black holes, and all sorts of things. I mean, they have a problem. They work with one force, and it only attracts. So how are you going to get things to squirt out energy like that? That's not like a garden hose. A hydraulic jet will dissipate. That's highly collimated over a distance of light years. Well, it turns out that in the laboratory, there's a thing called a plasma focus device, and it's a piece of cake to make a beam like that. And in fact, if we were to remove the back end of this thing and be able to somehow support the middle of it against gravity from falling apart, this back plate, unfortunately, is the only thing that holds the middle part there. But if you could remove that back plate, you'd get a double beam just like the one you see over there. Occam's razor says if there's a simple answer, at least consider it. And this is relatively simple. There's the artist's conception of what that thing looks like. That hourglass figure, here's an example of it. You can almost see the polar double layers along this polar axis. There's a phenomenon also, I didn't mention it in regard to the Birkeland currents, called the Z-pinch, which is when this thing, at places the two Birkeland currents can come together, form a very high intensity release of energy. And there's also a process called Markland convection, which happens at the Z-pinch, which accretes material. It accretes it much more efficiently than any accretion disk that astronomers seem to be able to come up with. My friend Tony Peratt says that he knows many astronomers at Los Alamos who've tried to come up with accretion disk models on the supercomputers there. and they do so only by adding plasma to them. Don't take it from me. That's what Tony Peratt tells me. But anyway, the Markland convection is a good way to do that. Here's over time, a picture of that nebula. And you can see that from 1989 through 2007, the number of double layers, if that's what indeed they are, here they're very easily, you can see there's 3 pairs of them here, very strong one at the top. So it changes over time. I'm sure astronomers will tell you, no, it's not double layers, it's shock waves. Well, okay. Here again is again that hourglass look, and if you use as an amateur astronomer, I use the phrase "use averted vision" if your eyes aren't good enough. You can also use averted imagination. I don't know. Well, maybe you have to use imagination here, but do you see some double layers, or maybe you want to call them shock waves? But there they are anyway. And this same sort of hourglass shape. And it goes on and on and on. There are many, many objects like that. This is the red square one. And you say, well, that doesn't show like an hourglass. Yes, it does. See the curvature here, and the curvature here, the curvature here, and the curvature there. I have some astronomer friends who said, look, Don, just because something looks the same doesn't mean it has the same causality. And that's right. That's absolutely right. But there's also another old phrase that says, if it walks like a duck and quacks like a duck, well. Here's Tony Peratt's simulations. This is a cross-section of a Birkeland current. Whoop, I'm sorry. Here, and that's how he started the simulation. He put in the simulation, he put Maxwell's equations. He also put Newton's law of gravity and let the thing go on in time. And eventually it ended up showing what looks like I think that's M81. I don't know. I don't know. Looks like a galaxy. Again, just because it looks like it, does it? No. But it's nice that this happens to have the same velocity profile, radial profile that does, without any dark matter or any other fairy dust. Winston Bostick at Los Alamos actually took 2 plasma focus devices and aimed them at each other like a pair of guys with dueling pistols, and actually created that rotating galaxy in the laboratory out of plasma, real plasma. Oh, his last quote. I have a copy of his paper, which I gave to Jan. And the last line in the paper is what you read at the bottom. So we don't expect these ideas to be instantly accepted. What we would like is to not reject them out of hand and just give them a look. And don't say you have if you haven't. Just give them an honest look. This is straight out of here. Goddard produced this picture of galaxies on a string. I don't want to get into the Big Bang business, but there's some questions about whether these structures are too big to be to accrete in the length of time that the Big Bang says the universe has been around. But I will submit that the formation of galaxies along intergalactic Birkeland filaments is consistent with Alfvén's model, Peratt's simulations, Bostick's lab experiments, Markland convection, and Z-pinches. So take it as you will. Oh, I don't know whether we have time to get into this pulsar business, but are they really rotating stars, or are they reflected waves riding on a plasma transmission line? We've all experienced the Northeast blackout. I'm old enough to experience both of them. And they were caused by pulses riding back and forth along a transmission line. And it's the easiest thing in the world in an electrical engineering laboratory to create a relaxation oscillator that puts out pulses, a kilohertz pulse. 1,100 times per second, it's 1 kilohertz. It's easy. It's a sophomore level lab experiment. The days when I was in school, we actually had a transmission line and we could measure those pulses and watch them go back and forth, and it was great fun. If you want to believe that you've got something the size 20 miles wide and the mass of the sun rotating about 1.5 times the speed of a dentist drill, you're free to do it. For me, it's beyond the believability curve. But especially when electrical processes can produce it so easily. I really highly recommend that paper. That is a paper written by Healy and Peratt in 1995. It explains 17, it replicates, they did an experiment in the laboratory with a transmission line, ran pulses back and forth, and replicated 17 of the known properties of pulsars. The frequencies are just as stable. Anyway, there's and this idea